Hello students. So this is a continuation lecture for business application of Maxima and Minima. In the first lecture of this chapter, we have completed single variable optimization. So in single variable optimization, we covered how to get maxima or minima, either for maximization of revenue or minimization of cost or maximization of profit. We have seen all the steps. Then we have also done what is equilibrium also. Equilibrium case also we have done. Equilibrium of firms. Equilibrium is nothing but maximization of profit. Now, the next important part in this chapter is multiple variable optimization. Students, my face may not be visible in this video. So in this video, only my screen will be visible to you. So just focus on the concept here. You need more attention. Multiple variable optimization means now in our equation, take this equation now, a is equal to x square plus xy plus y square. So we have x and y, two variables. So whenever your equation has multiple variables, multiple independent variables, right, how to get optimum point, that is maxima and minimum. So if our objective is profit maximization, then profit is dependent on joint impact of two independent variables. So let's say labor availability and sales demand. Or there are many variables, especially with respect to cost. It could be material also. Yes. So when your equation has more than one variable and your output depends on the joint impact of the two variables. So here profit maximization is the objective function, and the profit maximization depends on the joint impact of two variables here. One is the labor, the other one is sales quantity. So in such scenario, what we are going to do is we will solve the problem assuming that the other factor is constant. So in this case, what we will do is assuming one variable as constant when other variable is changing. So how we are going to solve this multivariable optimization is, first we'll take one variable constant. So first, if you are doing with respect to x integration, y we will assume constant. Then we will assume x constant, and then we'll do partial differentiation with respect to y. So for multivariable optimization, what we are doing is, since we have multiple independent variables, right, as inputs, now we have to solve that problem taking each one constant. First one variable, you should assume it as constant and then solve it. Then we should take other variable as constant and then solve it. Like if you have x comma y. So see this equation here. So above case, one variable constant, and then we'll take other variable changing. Similarly, again, next variable will keep constant, other variable changing. So this concept is only, we call it as partial derivatives. So in this case, we'll apply, whenever we have two variables, we have to apply partial derivatives. So see this example here. This is the equation. So in this equation, you can clearly see that there are x and y. That means two variables, independent variables. So in this case, how we should do differentiation, we see now. First, partial integration of this function a with respect to x we are doing. With respect to x, assuming y as constant here. We are assuming y as constant first. So we are doing partial integration with respect to x first. So now if I do partial integration with respect to x, which we can also call it as, show it as ax. So partial integration of x square with respect to x. And since y is constant here, so what we need to do, y into partial integration of, again, x with respect to x. And the partial integration of, this is how it is shown. This is partial, this represents the partial integration. the partial integration with respect to x of y square. So with respect now, why we are assuming constant here? So this constant always integration of constant is 0, and y into partial integration of x with respect to x is 1 only. So y into 1, y, and here it is like x power n. So n into x power n minus 1. So 2 into x power 2 minus 1, 2x. So 2x plus y is uh, the value for partial integration. First order this is. Assuming y as constant. Now again what you should do is, again the same equation, we need to do first order differentiation, partial integration, partial differentiation. With respect to y, we should do it, assuming x as constant. Now in this, I am assuming x as constant. So now partial integration of x square, partial integration of x into, then partial integration of y, then y square. In this, which one we are assuming constant? X, we are assuming it as constant. So partial differentiation of x square with respect to y is 0. The reason is we are taking x as constant, no? Yes. Then x into partial integration of y with respect to y is, because this is constant, this is 1 into x. And we are doing partial integration with respect to y only now. So y square means 2 into y. So this is with respect to y, we have done partial integration, assuming x as constant. So this is what you should do in partial differentiation. That is, in whenever you have multiple variables, this is what we should do. This is how we should do. The only difference between first single variable and multiple variable, if you see here first we need to solve with respect to x, assuming the other variable as constant, and then y with respect to y, assuming x as constant. This is the first order. Okay, after that, again we know that we need to have second order also. That is sufficient condition. That is, this is necessary condition. No? You have seen in the single variable optimization. This is second order we should apply. If you recollect, even in single variable also, we had this second order derivative, isn't it? So for the same equation now, you have done second order derivative. Now since we have to do with respect to y, with respect to x, right? So second order partial differentiation, you have to do this one again you have to do with respect to x. We call that as ax of x, that is partial integration of x of this one, first order derivative. Then the same you have to do with respect to y also, because every equation we are doing twice now, because every equation will have two variables now. So again this equation also has two variables, x and y. So again 2 times derivation, even second order derivation also, second order partial differentiation also, 2 times we have to do it for this one, because we have two variables, x and y. So second order partial differentiation with respect to x, again second partial differentiation with respect to y, we have to do it, same equation. And again the second one here, again this equation also, whatever we got earlier for first order, 2 times we have to do it. Why? Again this equation also has 2. So second order derivative of partial differentiation of y of x plus 2y. Again, with respect to y, what we will get? A y of x. So already we have this value now here. So that is the reason we are not doing it. So try to understand the second order. Second order is like the second order derivative what we have done for single variable. Same only. But since we have two variables here, we have to do twice. With respect to x, with respect to y, we have to do it. So when you do with respect to x, we are calling it as AXX. This is like a second time partial differentiation of the original one. Again, same equation with respect to y also we should do, assuming x as constant. That we call it as AXY. So if you see, already we got AX here. AX is nothing but partial integration of our objective function with respect to x. All right. So that is 2x plus y we got. Again, in this you have x and y. Now to do second order derivative, since again two variables are there, again we have to do with respect to x and y. So two times you will get. That is what I am trying to say here. So 2x plus y, again two times you will get. The partial integration of 2x plus y with respect to x, which we are calling it as axx. Again 2xy with respect to y also we should do it. See here y, 2x plus y. This we are calling it as xy. Now again, this equation is also there on x plus 2y. X plus 2y also with respect to y with respect to x. What is that? Partial integration of x plus 2y with respect to x. What we will get? What we call this as is ayx. So ayx or axy both will give same answer only. Let us check if you want. So partial integration of x with respect to x, again one will get. And here we are taking y as constant. So 2 into y into partial integration of 2 constant is, here it is 0. So it is 0. So we are getting answer 1 only. So same answer we got. So ayx or axy both will give same answer. So now you got 4 times. Second order you got 4 times. Because in first order we got 2 equations, no. So second order you will get four things. In fact, fourth one we have not done because that will be equal to axy only. Partial differentiation. Right. So this is what we should do. So this is only we have done second order partial differentiation. Now we have to check the conditions. Yes. Conditions also we should check for whether we got maxima or minima. So those conditions also we need to satisfy. So I was just doing the warm up for you for partial differentiation. When you get an equation which is having multiple variables, how we should do first order derivative and second order derivative. So what are the steps now for solving this multiple variable optimization? As usual, first we will have objective function. First one is objective function. That is either maximization or minimization. So if you take profit maximization, then that z is equal to, your equation will be like that. So this is the first thing, expression of the equation. Then first order partial derivative we have to apply. This is what in this equation we have done first time. Assuming, first with respect to x, assuming y as constant, which we will call it as here zx. Partial integration of equation z with respect to x, assuming y as constant. Then partial integration of z equation with respect to y, assuming x as constant. Assuming x as constant. And here assuming y as constant. Then once you do first order partial derivative, then if you remember even single variable optimization also, we have to find out the x value there. Here since we have y also, we have to find out x and y value by equating this above values zx, zy, that is partial integration of with respect to x and partial integration with respect to y. Both we should equate with 0 to get the x and y value, which we call it as critical values. All right. So once you get x comma y, then next step is do second order partial derivative, second order partial differentiation. Now, how many you will get? Actually, 4 you will get, but we are avoiding z, y, x because that value will be equal to z, x, y. So here, important thing is, now once you apply second order partial derivative, so in those values you substitute x and y. In those values, I mean the values of x and y you substitute in this zxx, zxy, zyy, you substitute those values. That is step number 3. Okay. So you're substituting, find value of these using the values of x and y calculated in step number 3. So before you substitute x and y in these values, first you get second order partial derivative. Once you get second order partial derivative, then substitute x and y in those values. Right? After doing that, then what we need to do is, this is the new thing. Since we have more than one here, values here, we need to apply determinants. So what exactly is determinants? What is the logic of that? Okay. Now, generally in regular class, I'll explain that. Now just remember that we have to find out a value called as D. Revision purpose. Just assume that we have to find out a value called as determinant. It is a checking condition basically, whether we got maxima or minima or not. That is what to check that, because now we have multiple, more than one we have now here. So that is the reason we have second order derivatives more than one. So whenever we have the second order derivatives more than one, we use these determinants. All right. So this, how we got this value, that I can tell you here. We calculate D, which we call it as determinant, by creating a matrix, which we call it as Hessian matrix. Remember this? What is the matrix name? Is Hessian matrix. Using the values of A, B, C. What is this A, B, C? The second order partial derivative of equation with respect to x, we are calling it, once you substitute x and y value, we are calling it as A. Then second equation also, if you substitute x and y value, whatever value you get, that we are calling it as B. And z, y, y, we are calling it as C. All right, so this is the equation. This is how matrix, this is Hessian matrix. A, B, B, C. So A into C, B into B. AC minus B square. So from there, this only we got this determinant value. D is equal to AC minus B square. So these we need to calculate. Value of D you should calculate. So once you calculate value of D, after that, interpretation we should do. See how many steps are there? 5 steps are there here. First one, equation, function, then first order partial derivative. 2 we will get first with respect to x, then with respect to y we will do. Then equate with 0 these two equations to get x and y value. Then again we will do second order partial derivative. So on this equation we will, on this value, 2 times we will get with respect to x and y. Again on this also we can do 2 times with respect to x and y. So whatever you get in those values, now substitute x and y, name them as A, B, C. ZXX name it as A, ZXY name it as B, ZYY name it as C. Once you do that, then calculate D value. D is equal to AC minus B square, which is based on Hessian matrix. Whenever you get this a square type matrix with 4 variables here, then you can use this Hessian matrix to find out the determinant. Once you find out the determinant, now we can check the condition, whether we got the maxima or minima. So how to do interpretation here? If D is greater than 0 and A comma C values, A value and C value is greater than 0 here, then there is a local minimum. Then there is a local minima. Here, slightly different from single variable optimization. So whenever D is greater than 0 and A comma C values is greater than 0, if it is greater than 0, then there is a local minimum. We say that at x comma y, we have a local minima. What is this local? I will tell you. Instead of calling it as minima, why we are calling it as local minima, I will tell you. Similarly, if D is greater than 0 and A comma C value is less than 0, we say that it is a local maximum. See, condition is same. Less than 0 means maximum condition only. No, greater than 0 is minimum condition only. No, that these are not changing. Okay, only D, that is a difference there. So when A comma C are greater than 0, we can say that local minima at xy. If it is less than 0, there is a local maximum. But D should be greater than 0. If D is less than 0, First of all, D value only less than 0. That means it is called as a saddle point. That means no local maxima, no maxima, no minima. That is like flat your curve in the graph. So then there is saddle point at xy if D is less than 0. If D is equal to 0, we say that the test has failed. If the D value is 0, we say that the test has failed. So this you have to remember for multivariable optimization. Okay. What is this global maxima or minima? Now, if you remember that graph, okay, this now we have multiple. See, this is maxima. This is also maxima. No, this is minima. This is also minima. Now, in this, all this highest point of highest point is out of this high point. This is also one high point. This is also another point. Highest high point is called as a global maxima. This is called as global maxima. Out of the highest points, the highest point we take it as global maximum. Out of the lowest point also, the lowest one we call it as global minimum. We call it as global minimum. So this is one global minimum out of the lowest, out of all values, lowest value is global minimum. Highest value we can take it as highest point is called as global maximum. This is called as local maximum, local minimum. Got it? So now, since we are having x and y, two variables now, we will get more than one value for x comma y. So we will have multiple maximas and multiple minimas here. So in this, what we should do is, the extreme one we should take. Since we have multiple maximas, out of that also highest we should take. That out of that highest we call it as global maximum. Similarly, out of the minimas also, lowest is called as global minimum. So in this, if you see in the diagram, which is the lowest here, this one is lowest. Global minima, this is global minima. This is global maxima, the highest and the lowest. And this one is local maxima, this one we can call it as local maxima. Local maxima. This one we can call it as local minima. Right. So whenever you have multiple variable optimization here, we'll get multiple maximas, multiple minimas. Out of that also we should take highest maxima, we call it as global maxima. Lowest minimum, we call it as global minimum. So when we say that global maxima or minimum we get, you can see the condition here. This is what you have to satisfy. When D is greater than 0, when D is greater than 0 and A comma C value is greater than 0, we say that there is a local minimum. When A comma C is less than, D is greater than 0, but A comma C is less than 0, then we say that there is a local maximum. Right? What is global maxima or minima is when we have multiple values for x comma y. Highest value of x comma y, we call it as global maximum. As I told you earlier, once we substitute x comma y, the highest values of x comma y, we call it as global maximum. The lowest value of x comma y, we call it as global minima here. All right. So these are the steps for solving a multiple variable optimization. So multiple variable optimization, what we have to do is the key point in multiple variable, because we have multiple variables. So we have to do partial differentiation. So first one variable assuming other one as constant, and then second time with respect to second variable, we have to do partial differentiation assuming the first one as constant. That is the key thing in multiple variable optimization. So let us do a problem now for this particular question. to understand all the steps here. So these are the steps here. Step number one is, again I am revising. Step number one, objective function. Then step number two is first order partial derivative. So 2 we will get with respect to x and with respect to y. Then equate with 0 those values to get x comma y. Then again second order partial derivatives for each, this one and this one again we have to do second time. So that means again 2 to this one 2 times, this one 2 times we will get. Actually 4 we will get, but y with respect to x will be equal to x with respect to y only. That is the reason we are not doing the fourth one. So whatever, once you do second order partial derivative of these equations, then substitute x comma y values there, get the values of those equations. Name them as A, B, C. Then calculate the value of D. D is equal to AC minus B square. That is derived from Hessian matrix. Okay, then you should do interpretation. If D value is greater than 0 and A comma C is less than, see whenever D is greater than 0, then we say that there is a local maxima or minimum. Whenever D is greater than 0, we can say that it is local maxima or minimum. And A comma C is greater than 0 means it is local minima, and A comma C is less than 0 means local maxima. What is the logic of this less than 0? Why it is called as maxima? Yesterday I told you. Downward bending indicates that it is maximum. All right. Now, when D is less than 0, it indicates it is a saddle point here. D is equal to 0, the test has failed. Now, let us do a question on this to get understanding. One equation here. See, directly question I will take here. Multiple variable optimization. Example now, say A is equal to, this is the equation given, okay, 50 minus 2x minus 5y plus xy. This is the equation. So in this equation, you have multiple variables x and y. That means partial differentiation we should apply. Yes. So just see now. First, step number one is first order derivative. So first order partial differentiation. First order partial differentiation we should do. With respect to x, assuming y as constant. So partial differentiation of A with respect to x first, assuming y as constant. So what is the value now? So partial differentiation of x with respect to 50 is a constant, no? 0 minus 2x value will be minus 2, because minus 2 into partial differentiation with respect to x is 1. Then we are assuming y as constant now here. We are taking y as constant. And this is also constant. The value will be 0. And y is constant, no? Y into partial integration of x with respect to x is 1. So the value will be y. So answer is here y minus 2, or we can say minus 2 plus y. We can call this as ax. So first we have done with respect to x, we have done taking y as constant. Now again we should do with respect to y the same. Partial integration of equation A with respect to y, we should do it assuming x as constant. Assuming which one constant? x as constant. So now the same equation, 50 anyhow constant 0. Now x is a constant. So constant 2 is also constant. So answer is 0. Then here 5 into minus 5 into partial integration of y with respect to y is 1 only. So into 1 means minus 5 will get plus here x is constant and the partial integration of y with respect to y is 1. So x you will get. So minus 5 plus x you will get. So this is partial integration of equation A with respect to y. So ax and ay we got now. First order partial differentiation is over. So this is how you should do first order partial differentiation. Then these equations we should equate with 0 to get x comma y value. Okay, first I will make you to learn how to get first order partial differentiation and second order partial differentiation. Now second order partial differentiation, I'm just making you to learn first order and second order. Second order partial differentiation. So Ax, nothing but partial integration of which one? This one, Ax. So what is the value of that? First we have to do again with respect to x. We are doing Axx is nothing but partial integration of which one? This one, minus 2 plus y with respect to x again. So what is the value of this? Minus 2 is a constant, 0, and we are assuming y as constant here. That is also 0. Now, same equation with respect to y we have to do it. Partial differentiation with respect to y. Minus 2 plus y. So minus 2 is a constant 0, and the partial differentiation of y with respect to y is 1. So 0 plus 1 is equal to 1. Alright, so first one we have done. Second order partial differentiation. Again, second equation also we have to do. So Ayx, that is partial integration of equation minus 5 plus x with respect to what? X we have to do it. So partial differentiation of 5 with respect to x is constant, no, 0. Then partial integration of x with respect to x is 1. So you can see we got same. Whatever we got for xy, even yx also we got same. So 1 only. That is what I was saying. So you need not do ayx. Then ayy. Partial integration of equation minus 5 plus x. With respect to y, we have to do it. So here minus 5 constant, no, 0. And partial integration of x with respect to y. X is a constant, no, here, no. So it is also 0. Answer is 0. So this you can avoid. This you need not do it. We can avoid. Because axy is equal to ayx value only. So this is second order partial differentiation. I hope now you understood first order partial differentiation and second order partial differentiation. So this is major thing when you are doing multiple variable optimization. Now I'll give you one question to understand the whole concept here. Example I am giving here for multiple variable optimization. A company produces two products X and Y. The total profit in rupees, in thousands, earned by the companies express. A company produces two products X and Y. The total profit in thousands earned by the companies expressed by the function. Algebraically, it is expressed by the function P is equal to 100x minus x square minus 2xy plus 200y minus 3y square. This is the equation. Which equation this is? Total profit equation they have given. They are producing two products X and Y, and the total profit earned by the company expressed in this function. This total profit function this is. Okay. Now find the profit maximization quantities of the products. That means X and Y values we have to find it. I mean X and Y value where the profit is maximum. So your quantities of the products means product X and Y. So at what level of output of X and Y the profit is, because two products now here, multiple products here. So multiple variables we have here. Yes. So find out that maximum profit also. Find out the maximum profit. Find out the maximum profit. So we have here equation. What is the equation here? P is equal to 100x minus x squared 2x minus 2x squared plus 200y minus 3y squared. That is the which equation? Directly the profit equation only now, because our objective is also profit maximization. And here x comma y represents the output of X, product X and product Y. So at what level of output the profit will be maximum, we have to get. So for that X comma Y values we should get, then comply with the condition. So let us apply the steps now. So this is multivariable question. Multivariable optimization question. So first let us take the equation. What is the equation given? P is equal to profit equation. This is 100x minus x square minus 2xy plus 200y minus 3y square. Now, first order derivative we should do. So P of x, that is partial integration of this P with respect to what? X, assuming y as constant. Y is constant now. So first partial integration of x with respect to 100x. 100 is constant, so 100 into, then with respect to x, partial integration of x with respect to x is 1. So 100 into 1, 100 minus partial integration of x square with respect to x is 2x minus. In this you have a y constant now. So first you should separate that y into, then 2 is also constant. So 2y into partial integration of x with respect to x is 1 only. So 2y only. Plus 200 is constant. Y is also constant. So 0. Y is constant here anyhow 0. So what we got 100 minus 2x minus 2y. So this is partial integration of the profit function with respect to x, assuming y as constant. Then again, with respect to y also we should do partial integration of equation profit p, that is with respect to y we should do it, assuming x as constant. Same equation now, x we are assuming constant now. So first 100x, x is constant, 100 is also constant, so 0. So x square is a constant now, 0. Because assuming x is a constant we are doing now. Next. So here x is constant, 2 is constant. So y with respect to y again 1. So minus 2x you will get. Then plus 200 is constant. So 200 into partial integration of y with respect to y is 1. So 200. Here minus 3 into y square with respect to y only, no. So 2y. So 3 into 2, 6y. So ultimately what we are getting is minus 2x minus 6y plus 200. So we got px and py, partial integration with respect to x and y we have done. Second step is over. Now this we should equate with 0 to get x comma y value. Yes, third one. Px is equal to 0 we will take first. So that is 100 minus 2x minus 2y is equal to 0. So now ultimately 2x minus 2y is equal to 100. How? Then take 2 common. X minus y is equal to 100. So x minus y is equal to 50. So this is, take this as one equation. Next, py is equal to 0. So directly you are not getting value. Py is equal to 0. That is minus 2x minus 6y plus 200 is equal to 0. So that means 2x plus 6y is equal to 200. Then take 2 common. So x plus 3y is equal to 200. So x plus 3y is equal to 100. This is, now what we have to do is, two equations we got. Now let's solve these two equations. We will get the values of x comma y. So solving 1 and 2. So x minus y is equal to 50. X plus 3y is equal to 100. So minus 4y is equal to minus 50. Therefore, y is equal to 25. So this is plus 3y, no? Minus y minus 3y minus 4y. 50 minus 100 is minus 50. So what is the y value? 50 divided by 4. This is If you do higher value, x plus 3y is equal to 100. Small x minus y is equal to 50. So minus cancel. So minus or minus plus, in fact, 4 is 50, yes. So what is the value of y I am getting here is x minus y is equal to 50. Other one is x plus 3y is equal to 100. So we are solving these two cases here. So what I've done is I've applied a minus no, because two equations solving means here 1 minus 2 only. So minus y minus 3y is minus 4y. 50 minus 100 is minus 50. So y is equal to 12.5 or 50 divided by 4. Fifty divided by 4. I hope calculation I have done correctly here. Now substitute this y value in x, the equation. You will get x value also here. Now here there is a small technical mistake I have made here. What is that? If you solve both 1 and 2 here, higher value is this one. So if you take first that one, 2x positive, this is here 2x value 2x plus 2y is equal to 100. This is that side. So if I take 2 common here, x plus y is equal to 100. Yes, x plus y is equal to 50. So this is your equation number 1. So small mistake what I've done is I took minus instead of plus there. So this is one equation, this is another equation. Solving now both 1 and 2, x plus y is equal to 50. X plus 3y is equal to 100. So minus minus minus, this one will get cancelled. Minus 2y is equal to minus 50. So y is equal to 25. So I'm getting y is equal to 25 now. Substitute this in equation number 1. Putting in equation 1, x value will be, equation 1 if you put x plus y is equal to 50, x value will be 25. Put y is equal to 25 in equation 1. So we got x value, y value. So this is only we call it as critical value. Critical values are 25 comma 25. Okay, now second order partial we have to apply now. Yes. Step number 4 is second order partial differentiation. Second order partial differentiation we should get. Second order partial differentiation. For this equation now, this equation with respect to x and y we have to do it. For this equation only if you do with respect to y, that would be sufficient. So 3 we have to calculate here. What are those? So first p x, it is nothing but partial integration of this equation 100 minus 2x minus 2y with respect to x. 100 minus 2x minus 2y with respect to x. Let's call this as pxx. Next, so 100 is a constant, so 0. So partial differentiation of 2x with respect to x. 2 is a constant, minus 2 into 1, this is minus 2. And y is a constant now here. Assuming y is a constant, we are doing this. So 0. No. So minus 2 we are getting. Let's call this as a. Next, same equation with respect to y we have to do it. So pxy we will call this as partial integration of same 100 minus 2x minus 2y now. With respect to y, that is assuming x as constant now. Now you assume x as constant in this. So 100 anyhow constant 0. X also we are assuming constant, 2 is also constant, so 0. Now minus 2 into partial the differentiation of y with respect to y is 1. So answer is minus 2. So we will call this as B, capital B. Next. Now second equation, that is this one. With respect to y only you solve it because already with respect to x values here we have. So we can call this as P y with respect to y only we can do it C. The partial integration of this equation minus 2x minus 6y plus 200 with respect to y you do it assuming x as constant. So x is constant, 2 is also constant, 0. Minus 6 into partial integration of y with respect to y is 1. Constant, so 0. So minus 6. So directly we got values here for the second order partial differentiation. At critical values 25, x 25, these are the values we got. So without substituting them directly, we got the values only here. Now, step number 5 is determinant we have to find out. D value we have to find out here. D is equal to, now we need not do here Py of x because Py of x value will be equal to Pxy only. That is the reason we are not doing that. Now D value determinant is equal to AC minus B square minus B square. So what is the A value we got here? Minus 2. Minus 2 into C value we got minus 6 minus B square. That is minus 2 square. So minus 2 into minus 6 is 12. Minus 2 square, the minus 2 square is 4. So 8. So D value we are getting greater than 0. So that means definitely there might be a local maxima or minimum. So D value is 8. Now A comma C value is, both are negative, that is less than 0. So less than 0 means it is maxima only, no, local maxima we have. So as, now we need to check the condition as D is greater than 0 and A comma C less than 0, no, both you can see A is minus 2, even C is also minus 6, less than 0. So what we can see is now there is a local maxima. Therefore, there is a local maxima at x is equal to 25 and y is equal to 25. See, unless here specifically asked here global maxima, you need not write. Local maxima only you can write. Okay. Now, so we basically what we are saying here is The profit will be maximum at what? When x is equal to 25 units, y is equal to 25 units. Now maximum profit is equal to, substitute in profit equation. Hundred x minus x square minus 2xy plus 200y minus 3y square. So substitute no x and y value. 100 into 25. 25 square minus 2 into 25 into 25 plus 200 into 25 minus 3 into y square means 25 square. So ultimately what is the answer you will get for this is 3,750 in thousands this is. Okay, because profit is in given in the question, no? What I have given profit? Total profit in thousands this is. So whatever we got also profit is in thousands. So this is the complete solution. I hope you understood all steps. No? How many? 5 steps. All 5 steps we have done here. So this is multiple variable profit maximization. Okay. Yes. Now even in multiple variable also we have equilibrium, monopolistic firms. Even with multiple variable optimization also, equilibrium of a monopolistic competitive firm in multiple variable scenario we have to learn. Like even in single variable optimization also we have done monopolistic competitive firm. Equilibrium is nothing but profit maximization also, no? So it is like profit maximization only with multiple variable optimization. Now in this, 2 types are possible here. One is multi-plant producing, a firm having multiple plants producing the same product at different costs, because each plant is, I mean, at each plant the cost is not same. So this is the first scenario. So a monopolistic firm having multiple plants but producing the same product at different cost. This is different, multi-plant and different cost. At each plant the cost is not same. So this is one scenario. In this scenario, how to get equilibrium? Other scenario is multi-market. Market is different. Different markets they're selling at different price, but same product is sold. So that means there is a price discrimination. So these are the 2 cases. In these 2 cases, how do you get equilibrium? Maximum profit. So what is the price they should charge here? Let's understand each scenario and then steps, because steps will not change, steps will remain same. The first case is multi-plant producing the same product at different costs. So it is a monopolistic firm, basically industry. Now they're having multiple plant, and at each plant they're producing the same product only, but at different costs. Now they want to know what quantity they should produce in those plants to maximize the profit. That is what equilibrium means. Okay, that is a scenario. In these multiple plants, now they are going to produce, at each plant they are going to produce output or not. So how much if they produce, how much they have to produce of the product to maximize the profit. So that is what we have to achieve. That is our objective in this scenario. So now since they are having multiple plants, assume now they have 2 plants now. Assume we have 2 plants, plant 1 and plant 2. And assume the output produced there is X1 and X2. Assume the output produced is X1 and X2 at the respective plants. Since it is same product only, X1, X2 is only output, but they're producing the same product. Yes, so if I want total revenue now, I can add both X1 and X2 now. Then that will become my total quantity produced at both the plants. So X1 is the output produced at P1 and X2 is the output produced at plant 2. Assume 2 plants now. Okay, so when you have 2 plants with different costs, we will have 2 different cost functions. One is at plant 1 and other one at plant 2. So plant 1 we can call it as total cost 1, plant 2 we can call it as total cost 2. Alright, because we have two plants, different costs, so that is the reason two cost equations will be there. But revenue we will have only one equation. Why? Because same product you are producing. Easily we can add the quantities at both the places. X1 at one plant, X2 quantity at other plant. These two we can add because it is the same product. So total revenue, how do you get? Price into quantity. Here P is price and quantity is a combination of sum of both X1 and X2. Now, so that means only one total revenue. Why we are taking total revenue and cost is because profit we want, no. Ultimately, equilibrium is nothing but maximization of profit. So what we can do is, now we require total revenue. Total revenue means, how do you get total revenue? Price into quantity. Price what we are charging is same only, but the quantity is not same at two plants. So that is X1 and X2. So this is total revenue equation. So now first we need to set the equation or not. Set equation is total revenue. This is only the first equation. But so that is not the first equation because profit maximization is the objective, no? So how do you get profit? Profit is equal to total revenue minus cost. Total revenue minus cost. But cost we have two functions now. Cost 1 at plant 1, cost 2 at plant 2. So if you remember now, in single variable optimization also we had equilibrium there. So there I gave you two options to do that problem. One is with respect to total profit or separately revenue, separately equation. I mean separately cost. You can do integration, partial integration you can do. So what you can do in this scenario is first you get MR with respect to total revenue. Okay, then with respect to cost, we have two cost functions now here. One is at plant 1 and plant 2. Then get MC1 and MC2. MC1 represents the first order derivative of total cost 1. And second one represents a first order derivative of plant 2 total cost. So MR, MC1 and MC2. At equilibrium, we know that these three will be what? Equal, no? This already in single variable optimization also we have done. MR is equal to MC or not? MR minus MC is equal to 0. MR is equal to what? MC. So like that here, MR is equal to MC1 is equal to MC2 at equilibrium. So now to get X value and Y value here, X1 and X2 values, we have to equate this. MR is either MR is equal to MC1 you can equate, or MR is equal to MC2 you can equate, or MC1 is equal to MC2 also if you equate, then you can get X1 and X2. Once you get this X1 and X2, now we have to check whether we got the maximum profit or not. So for my maximum profit, what is the condition? Condition is your MR, second order derivative of MR must be less than what? Second order derivative of MC1. And again, MR should be less than what? Second order derivative of MR must be less than second order derivative of MC2. That is at plant 2. Because at both the plants, this condition must be satisfied now. If you want to achieve maximum profit, to say that there is a maxima, here, your MR must be less than what? Your second order of MR must be less than MC1. Go back to single variable optimization, equilibrium scenario. This is what I told you. You need second order MR must be less than second order what? MC I told you, because we have two plants here. So two conditions separately we have to satisfy. If MR, second order derivative of MR is less than second order derivative of MC1, and the second order derivative of MR is less than MC2, then we can say that there is a maxima there. Okay. So now in MR only, in marginal revenue only, if you write instead of X, if you substitute X1 and X2, then what we have to do is Then with respect to x1 we have to solve, and with respect to x2 also we have to solve, because we have multiple variables now, x1 and x2. So if equation has both x1 and x2, then we have to solve with respect to x1, and then we have to solve with respect to x2. So this is the first scenario, that is multi-plant producing the same product at different cost. Okay, now this, to explain these steps, these are the steps involved now. Single variable equilibrium, if you have done, easily you might have understood this. Only thing is, instead of one cost function, we are having two cost functions. The reason is we have two plants now with different costs. Revenue, only single function I am taking. The reason is both we can add now. One single product only are producing at both the plants. Okay, let us solve one question here. I'm taking one question from Institute Metal only. This is the question. You should also identify the question. Single variable optimization. So this is one question. A manufacturer produces liquid commodity at two different plants. Yes. Located in two regions of the country. The selling price in rupees per liter of the product is given by equation P is equal to, where X is equal to X1 and X2. Total production of two plants together. X1, X2 represents the production together now of both plants. Cost function of the two plant is also given. C1, C2. Determine the quantities produced by two plants, which will put the manufacturer into an equilibrium condition. See here, perfect scenario. This is only the scenario, no? So monopolistic form in two different plants. He's producing the same product. Now his objective is to maximize the profit. What output they should produce at the two plants? Is there no? Yes. So this is the perfect question now for our concept. Now to solve this, what we require now? Either we have to, now we will use this MR, how many equations, cost equations we require? How many cost equations we require here is? Two cost equations we require. What are those two cost equations? One is this one, other one is this one. Okay, so this is the question I'm taking here, your institute question only. Illustration 6, CMA material. To explain this multivariable, multi-plant, illustration 6, CMA material. To explain equilibrium. Multi-plant equilibrium. First, total revenue, TR, is equal to price into quantity. Okay, this is how we will get total revenue. You all know this. Let's take now, what is the price equation given in this question? P is equal to 200 minus 0.8x. 200 minus 0.8x into quantity we are treating as x only. Total quantity together we are taking, where x is equal to x1 plus x2. X is equal to x1 plus x2. But I am not taking x1 and x2 here. Directly what I am doing is, I am putting x only because x is together, no, both x1 instead of including two variables. I will include only one variable so that we can use only single derivatives instead of partial derivatives. Okay. Now, so I'm taking directly x quantity. X includes both x1 and x2. Now, what is your total revenue? 200 into x is 200x minus 0.8 x square. So this is your total revenue. Okay. Now, what we require? MR we require. MR is nothing but first order derivative. In this, you have only one variable, no? So derivative you can apply, not partial derivative. That is advantage by not taking x1 and x2 in this equation. Okay, even if you take x1 and x2 also, we'll get the same answer only. But quickly we can do. We take this single only. So now MR is equal to, MR is nothing but d by dx of total revenue. So this is derivative only. D by dx of TR is, so 200x, 200 into d by dx of x is 1. So 200 minus 0.8 into 2x. So this is 1.6x. So this is your first order derivative. This is MR. Okay. Now, next thing is, what else we require? Step number 1. Even total cost also we require now. Two plans are there now. Each plant have different cost functions. So total cost of plant 1 is given by TC1 is equal to 0.3x1 square 600x1 plus 5000. This is also having only one variable in it, x1. So C1 is equal to 0.3x1 square plus 60x1 plus 5000. It is having only one variable now, that is x1. So only derivative you can apply. So MC1 is nothing but d by dx1 of which one? TC1. So tell me what is the value of this 0.3 into 2x1. So 0.3 into 2x1 plus 60 into x1, d by dx1 of x1 is 1. 60 into 1 plus 5000 is constant 0. So this is 0.6x1 plus 60. This is MC1 for plant 1. Now we have another cost now at plant 2. Total cost at plant 2. 0.5x2 square given 30x2 8000. So now again first order derivative for this. So MC2 I want now. So d by dx2 of total cost at function of plant 2. So minus 5 into 2 1x2 plus 30 into 1 plus 0. So this is x2 plus 30. So at both the plants total cost we have done first order derivative. Remember here there is no partial derivative. Why no partial derivative here? Because each equation has only one variable. No, that is the reason. Okay, this is your step number 1. Now step number 2 is we have to find out the x1 value, x2 value. Now for that what I told you, at equilibrium situation TR is equal, MR is equal to MC1. Either you can equate this or MR is equal to MC2 or MC1 is equal to MC2 also if you equate for x1 and x2 we have to equate this. So what we are doing is one equation, first one we will do it. First MR is equal to MC1. What we are taking, MR is equal to MC1 I am taking. MR is equal to MC1. So what is the MR we got? 200. 200 minus 1.6x is equal to MC1 we got 0.661 plus 60. plus 60. This is MR is equal to MC1. Similarly, MR is equal to MC2 also we will take. Why I'm not taking MC1 is equal to MC2 is MC1, MC2 you have directly X1 and X2. There is no possibility there. So that is the reason always you take this only. MR is equal to MC1 and then MR is equal to MC2. MR 200 minus 1.6x is equal to X2 plus 30. Now, we solve these equations. What you are getting? Now here what you can do is we know that x1, x2 if you want to get x is equal to, we know that x is equal to x1 plus x2 or not. So here we can substitute those values. Instead of substituting here and making it a partial derivative, here only we can substitute. So 200 minus 1 point into x place x1 plus x2 is equal to 0.6 x1 plus 60. Okay. Or even MR, MC1 is equal to MC2 also if you substitute there, still we get the answer. So now, so 200 minus 1.6 x1 plus, no, minus 1.6 x2 is equal to 0.6 x1 plus 60. So minus 1.6 minus 1.6 is minus 3.2 minus 3.2 minus 6, okay, 3 x1 minus 200 minus 60 is 140. X1, so I should not add these two, no, because this is x1 and x2. So minus 1.6 x1, this it comes this side minus. So 1.6 to 1.6 is 2.2. So this is minus 2.2 x1 minus 1.6 x2 is equal to minus 200, if it comes to this side, minus 140 minus 200 plus 60 is minus 140. So how we can write this one? 2.2 x1 plus 1.6 x2 is equal to 140 minus, that side, this side we can cancel by taking common there. So now if you take in this 1.6 common, or let it be, this is one equation, equation 1 again. Here also you substitute 200 minus 1.6 into in x place. We know that x is equal to, x represents the total quantities of at plant 1 and plant 2, x1 and x2 is equal to x2 plus 30. So 200 minus 1.6 x1 minus 1.6 x2 is equal to x2 plus 30. Right now, minus 1.6 x1. This one is minus 0.6 x2 minus 1.6 minus x2 now. So minus that is not 1.6, that is minus 2.6 x2 is equal to, if this 200 goes to that side, or let us retain this 200 this side only. 200 minus 30 is 170. So 170 is equal to, take this to that side. This will be positive 1.6 x1 will be positive plus 1.6 x2 plus this one x2 plus 2.6 x2 plus 2.6 x2. So this is equation number 2. So two equations we got out of this. Now we have to solve these two equations. So 1.6 x1 plus 2.6 x2 is equal to 170. Other one is 2.2 x1 plus 1.6 x2 is equal to 140. Now one we have to cancel now here. How to do that is, if this has to 1.6 has to become 2.2. So 2.2 divided by 1.6, how much we are getting? 2.2 divided by 1.6 is equal to 1.375 we are getting. Or what you can do, you can cancel this one also, or 2.6 divided by 1.6 also you can do. 1.625 you can multiply. So anything to make them equal. So what I am doing is, this equation I am multiplying with 1.375 and multiply. Let's see what happens now. 1.6 into 1.375 will be 1.6 divided by 2.2. 1.6, 1.375. So this will be 2.2x1 plus 2.6 into 1.375, 3.575 x2 is equal to 170 into 1.375, 233.75. Now this equation will be same only, 2.2 x1 plus 1.6 x2. I'm multiplying both sides with the 1.375 there, so that I can cancel 1. 1.6 x2 is equal to 140. Now minus, minus, minus. This one will get cancelled. Now 3.575 minus 1.6. 1.975 x2 is equal to 233.75 minus 140. 93.75 we are getting. Therefore, x2 is equal to 93.75 divided by 1.975. 47.47 we are getting. x2. x2 we got 47.47. Now, if you substitute this in x1, I mean, first equation, therefore x1 is equal to 2.2 x1 plus 1.6 x2 we got 47.47 is equal to 140. So 2.2 x1 plus 1.6 into 47.47, 75.952 is equal to 140. 2.2 x1 is equal to 140 minus 75.952. 64.048. X1 is equal to 29.11 I am getting. So we got X1 and X2. X2 47.47 units. At plant 2 you should produce 47.47 units. X1 plant 1 you should produce 21.11 units. Now this is your X1 and X2, step number 2 only. We equated to get X1 and X2. Now what is the condition? Second order derivative also we should do. Yes. Third step is second order derivative, because the first one is in single variable only we have. No, so first second order derivative of mr, d by dx of mr we will do. So nothing but d square by dx square of tr. This is nothing but what? D square by dx square of tr. So d by dx of what is the mr we got? Marginal revenue 200 minus 1.66. Why we have to do second order derivative? To confirm whether it is a maxima or minima or not. So here it is maxima, no. So d by dx of constant is 0 minus 1.6 into 1. So we are getting minus 1.6. So we are getting d by dx of mr value is minus 1.6. Next, we also want d by dx of mc1 also. You have to prove that mr is less than mc1. Slope of mr is less than slope of mc1. So d by dx1 of mc1, what we got? Plant 1 first order derivative 0.6x1 plus 60. 0.6x1 plus 60. So what is the derivative of value of this? 0.6 into derivative of x1 with respect to x1 is 1. So 0.6, constant is 0. So mc1 also we got. Similarly, we should also get d by dx of mc2 also. So d by dx with respect to x2, because we have x2 in that variable. mc2 we have x2 variable. How much we got? x2 plus 30. So that second time we have to do derivative. So x2 with respect to x4 is 1. That is 0. So we got mc2 also. Now what is the condition we have to prove for maximum? mr should be less than mc1 as well as mc2 or not. So minus 1.6 is less than 0.6 and 1 only directly. So easily we are able to finish off quickly here. Otherwise, if you keep x1, x2 in the first TR equation only, in this equation only, instead of x here, directly if you take x1 and x2, so you have to apply partial there because it will have x1 and x2. Then again, second time also, again we have to get 4 and then d value also we have to do. So instead of all that headache, what we have done, shortcut we use. Directly we retained x only. Only when you are getting the value of x1, x2 only, we substituted there in x value. That is a smart thing we have done. Otherwise, it will become a very long problem. That also I will show you here. So now MC2 we got. So therefore now, since now d by dx of MC1, MR is less than d by dx of your MC1. And also d by dx of MR is also less than d by dx of marginal cost of plant 2. So therefore, what we can say, there is a maximum. There is a maximum. So the maximum profit what is the maximum profit output level? At x1 is equal to 29.11, x2 is equal to 47.47, profit will be maximum. So profit maximizing output we got. That is what the question requires us to find out. See the question now. Determine the quantities to be produced by two plants, which will put the manufacturer into an equilibrium condition. Nothing but maximization of profit. So what is the answer? We got 29.11, 47.47 we got. Rounding off, they rounded off to 5 liters. 29.11 we got. 29.1 they have taken. So now the same question, what you can do is here, partial differentiation also we can do. When, see here, now alternatively here what we can do is, if you want to apply partial differentiation, how you can apply partial differentiation, tell me. If MR is written as, in MR equation only, with two variables, I told you earlier. Here instead of x, if you take directly x1, x2, there only in TR equation only, then it will become partial differentiation. If MR is written with two variables, so MR is equal to then 200 minus, here we should use what? Partial derivative. Okay. So then what you can do is MR we got 200 minus 1.6 x no, so x1 plus x2. So this only now MR is equal to 200 minus 1.6 x1 minus 1.6 x2. Now MR has two variables x1 and x2. So when you are doing the second time derivation, second order derivative, now partial we should apply because we have two, no, x1 and x2. So two times we have to do it. One is with respect to x1, then other one is with respect to x2. So partial integration now, because two variables, partial integration of MR with respect to x1, with respect to x1 first. So x1 if you are doing now, x2 will become constant. So first 200 is constant anyhow 0. With respect to x1, minus 1.6 into 1, minus 1.6. And x2 is anyhow we are assuming it as constant, it is 0, minus 0. So we are getting minus 1.6 only. Now again, partial integration of MR with respect to what? x2. Assuming x1 as constant. So 200 again 0. Now here x1 is constant, so it is 0. Now x2, with respect to x2 only we are doing partial integration. So 1 minus 1.6 into 1. So we are getting minus 1.6. So with respect to x1, with respect to x2, we are getting same. So now what is the condition you should satisfy is partial integration of MR with respect to x1. This is plant 1 revenue, no, marginal revenue, second order derivative of plant 1. It should be less than the plant 1 marginal cost, second order derivative of MC1. This condition must be satisfied. Similarly, plant 2, what is the MR? Second order partial derivative of MR with respect to X, what we got, that should be less than plant 2 second order derivative of plant 2. If this condition is satisfied, then that is only maximum. That is what exactly happened there. So if you substitute x1 and x2, then do partial differentiation, then this is a condition you have to check for to say that it is a maximum. Instead of that, what we have done, separately we have taken MR only we have shown. Directly MR only we have compared with MC1 and MC2 because we did not substitute x1 and x2 there when you are doing this second order derivative. Okay, so this is your equilibrium with multiple plants. Equilibrium with multiple plants. Let's go back to that chart. In this one we completed multi-plant producing the same product at different cost. So two cost equations you will have, one revenue equation, that is what you should remember. Okay. Now the other scenario is a monopolistic firm is selling the same product in multiple markets, in different markets with a different price. Now, for them, the dilemma is what is the price they should charge there? What is the profit maximizing price? So in those markets, what is the price they should charge to maximize the profit? That is only equilibrium. That is the condition here. So multi-market selling the same product at different prices. So that means now we have two separate markets. Each market will have separate revenue. No? So we have two revenue equations here. And two separate prices also we will have, because each market, the price is not same. Okay, so remember here in this scenario, you have multi-market firms selling in different markets, same product at different price. So if you assume that now two markets, so that means in two markets, product is same, but the quantity may not be same and price is also not same. So what you will have is two separate revenue equations you will have. You have two markets. And even price also you have two separate prices, because the price is not same in both the markets. So in that case, what are the steps is, first MR1 we have to find out. So nothing but d by dx1 of TR1. MR2 also you have to find out. That is d by dx2. Now because we are having only one variable here, we are applying the first order derivative. Okay, observe the difference here. So d by dx2, what is MR2 is nothing but first order derivative of total revenue at second market. And cost we can take only one. Even though you are selling at different markets, but the cost remains same only. Price is not same, but cost is same. The cost, total cost we can take same. Because you are producing only single product, you can add all the costs in different markets. So MC will remain only one. So how to get MC? D by dx of the total cost. So this is the first equation. These are the equations you should get, values you should get, step number one. Step number two is at equilibrium, these three will be equal. MR1 will be equal to MR2 is equal to MC. Now to get X1 and X2, you have to equate this. Either you have to equate MR1 with MR2 or MR1 with MC or MR2 with MC. Then to check for maxima, what are the conditions you should satisfy? The slope of MR1 here, that means second order value of MR1 must be less than the second order of MC. For maxima, these are conditions we should satisfy. No? Similarly, now revenue are two markets. No, cost is only same. So again, the second order, the partial differentiation, second order derivative of MR2 must be less than second order derivative of MC. So then we can say that there is a maximum. So these are the three steps you should apply. So this is a very important problem now for coming exam. Even recent exam also they have covered this. So let us see that question now. You see the question, you can identify that scenario. See this question now. This is the question. Illustration number 7, CMM material. Monopolist, a discriminating monopolist. A discriminating monopolist is able to separate its customers in two markets. A discriminating monopolist is able to separate its customers into two markets with respective demand functions. So clearly you can see that two markets they are given. X1 given by two demand functions. So this is what the quantity what they are producing in market one, quantity what they are selling, X1 represented by X1. And this is the quantity they are selling in market 2. So these are the two markets. So this is the demand in market 1 and market 2 represented by x1 and x2. It's like quantities. Market 1 x1, market 2 x2. Total cost function. So these two markets together cost they have given 20 plus 20x. Here x is consisting of x1 market quantity and x2 market quantity. Both together is only x value here. X is nothing but that only. So now you will have two revenue equations and one cost equation. Determine the equilibrium price of the product in the two markets. That means here in two market, what is the price they should charge to get the maximum profit. Also determine that equilibrium profit. Otherwise, find out the maximum profit also. So in these two market, what is the price they should charge? In these two markets, what is the price they should charge? That is what we should find out. So how many, tell me how many equations here? Revenue equations, you will have two equations now. One is market 1, other one is market 2. How do you get revenue? Price into quantity. So illustration 7, this is next scenario. This is multi-market equilibrium. Illustration 7, multi-market equilibrium. CMA material. This is the last one now. CMA material. Multi-market equilibrium. We have to find out equilibrium situation. So step number 1 is first revenue. We have to take equations. Step number 1. Total revenue of first market is equal to price into quantity. No. So price in that we are assuming it as P1 and quantity is X1. And this is first market total revenue equation. Represented by first market, what is the price? Now prices are also different. Now that is the reason separately we are taking. Remember, identify the difference between previous question and this question. So here, since we have two markets, price is not same. No, that is the reason we are differentiating P1 and here the quantity is X1. So have they given P1 equation in the question? Yes. They have given P1 also. If you see in this question, have they given P1 is not given here. They have given P1 function is not given, P2 also not given. So we can get that, but they have given one equation here. What is that? X1 they have given. No. From this we can get P1 and P2. See here how to get that. X1 they have given, X1 is equal to demand function they have given. No. 16 minus 0.2 P1 they have given. So from this we can get P1. 0.2 P1 is equal to 16 minus X1. So P1 is equal to 16 by 0.2 minus X1 by 0.2. So therefore P1 is equal to 80 minus 5x1. 80 minus 5x1. So what is the P1 here? 80 minus 5x1. This is our P1 value. And x1 represents the quantity at market 1. Okay, this is very, so framing the equations here very, very important. In this question, they have not given price equation separately here. They have given quantity equation, demand, which included price. So from that we derived P1. So 80x1 minus 5x1 square. So we got TR1. Now we should get MR first order for this derivative. Why only first order derivative? Why we are saying? Because it includes only one variable. So I want MR1. MR1 is nothing but d by dx1 of TR1. So tell me, 80 x1 is with respect to x1 is 180 minus this one is my minus 5 into 2x1, so minus 10 x1. So MR1 we got for market 1. Next, now second market, total revenue first we should get. Price we are taking as P2, quantity is x2. Okay, now again P2 directly they have not given equation, but they have given x2 equation. X2 is equal to 9 minus 0.05 P2. So from this we can get P2. 0.05 P2 is equal to 9 minus x2. So P2 is equal to 9 by 0.05 minus 1 divided by 0.05 x2. So therefore P2 is equal to 180 minus 20 x2. So now substitute now P2 value is 180 minus 20 x2 into x2. So this is 180 x2, 180 x2 minus 20 x2 square we got. So now first we should apply first order derivative. We call that as MR2. So d by dx1 of, sorry, dx2 of your total revenue, if you do, we'll get our first order derivative. So how much is that? X2 with respect to x2 is 1 only, no? 180 into x2 with respect to x2 is 1. So 180. Then minus 20 into x2 square. It's like x power n, no? N into x power n minus 1. So 20 x2 minus 20 into 2x2. So 40 x2. So 180 minus 40 x2. So I got now first order derivative of your two markets revenue. And also now one more thing what I want, because profit maximization we want to. Now cost function also we require. Now cost function only single function we are taking, because in both the markets, since you are selling the same product, so I can summarize the, I can get the sum of the cost. So TC is equal to first total cost is equal to, what is the equation? That equation they have given 20 plus 20x. This is the equation they have given. So get the first order derivative for this. This includes again only x. Now what I'm doing is I'm not substituting in x1 plus x2. If you do that, then you have to apply partial derivative. So what we can do is, instead of substituting in this x1 and x2 at this time, okay, later on we can substitute to get x1 and x2 value, not now, so that we can quickly finish off the problem. So now MC is equal to d by dx of TC is equal to 20 is a constant 0. X 20 into x is 1. 20 into x with respect to x is 1. So 20. So into 1. So 20. So now we are ready with the first order derivative values. Now we have to equate with equilibrium, means we can equate with what? Step number 2. TR1 is equal to MC. No, not TR1, MR1. MR1 is equal to MR2 is equal to at equilibrium MC or not. So now MR1 is equal to MC. MR2 is equal to MC. Equate. What is the MR1 value we got? 80 minus 10x1 is equal to what we got? MC. MC, this one, 20. So 80 minus 20, 60. X1 is equal to directly 60. 80 minus 20, 60. 60 divided by 10 is 6. X1 is equal to 6.
MR2, how much we got? 180 minus 40 x2 is equal to MC is 20. 180 minus 20 is 160, and that side 40. 160 divided by 40 is 4. So x2 is equal to 4, I'm getting. So x1 and x2 we got now. Now we should get the second order derivative of MR1, MR2, and TR2. Isn't it? To get the maximization condition satisfied. So next step is that only. Third one. D by dx 1 of MR1, second order derivative, is equal to D by dx 1 of MR1. How much we got? 80 minus 10 x1. So with respect to x1, 80 is constant 0. First order derivative of x1 with respect to x1 is 1. Minus 10 into 1 is minus 10. So answer is minus 10 here. So d by dx1 of mr1 is minus 10. Next, d by dx1 of mr2 also we have to do. So d by dx, so here x2 no. D by dx in mr2 means x2 no, because market to quantities x2. With respect to what is the equation we got? 180 minus 4, 180 minus 4x2. Not 4, 40. 40x2, yes. So 180 is constant 0. 40 into x2 with respect to x2 is 1 minus 40. So minus 40 we got. So mr1, mr2, second order derivative is over. Now what is the other one? Second order derivative, mc second order derivative. So d by dx. In mc we have x only, no? MC is anyhow constant, x only we have. So d by dx of MC. So d by dx of 20 is constant, no? 0. So now mr1 is less than 0, mr2 is also less than 0. That means what? Our condition is satisfied for maxima. So d by dx of mr1 is less than d by dx of mc, and d by dx2 of mr2 is also what? Less than d by dx of mc. So this is the condition for maximum. So there exists maxima here. Maximum. So now profit is maximum at x1 is equal to 6 and x2 is equal to 4. x1 is equal to 6. This is what we got now. So at these values, at critical values, the profit will be maximum because this condition is satisfied now. And they also asked in the question, we got 6 and 4. Let us check the answer now. You can see answer is 6 and 4. And in the question they have asked to find out equilibrium profit, nothing but maximum profit. So profit is equal to maximum profit. How do you get profit? Total revenue minus total cost. Your total revenue consists of two market revenue. No? Total revenue at market 1, total revenue at market 2 minus total cost is only 1. So what is the total revenue at market 1 equation? We have to take that full equation. Total revenue equation is 80x1 minus 5x1 square. At say market 2, 180x2 minus 20x2 square. This is total revenue equation. This is at market 2. Minus total cost equation. 20. What is the total cost equation? We got 20 plus 20x. 20 plus 20x. So now in this you should substitute values, x1 value and x2 value. So this is equal to 80 into x1 value is 6 minus x1 square means into 6 square plus 180 into 4 minus 20 into 4 square minus 20 plus 20 into here x means what we should take. X means x1 plus x2. X means here x is equal to x1 plus x2. No, wherever x is there, x1 plus x2. So what is x1 plus x2 both together? 10. 6 plus 4, 10. If you solve this, you will get the value. So 80 into 6 is 480 minus 6 square 36 into 5 is 180 plus 180 into 4 is 720. 4 square 16, 16, 23, 23,200, 320, sorry. Minus 20 plus 6 plus 4, 10, 10 into 20, 200. So 480 minus 180, 300 plus 720 minus 320 is 400. This is 200 plus 20 is 220 minus 220. So answer is 480. The answer is maximum profit is 480. Let's check now what is the maximum profit. Determine the equilibrium price of the product and also determine the equilibrium profit. So price we got correct on x1, 6, x2, 4. This is a price. Condition satisfied. Sorry. One mistake I've done. What is the mistake here? Whatever we got x1, x2 is quantities now. Here, x1, x2 is quantities no. Profit is correct only. Our answer is profit is correct only, but question requirement is what they asked you to find out prices, not the quantities. X1, x2 represents quantities no. So what is the price equation? We got price equation. This is the price equation. P1 is equal to 80 minus 5x1. P2 is equal to 180 minus 20x2. These are price equation. So equilibrium price you substitute. 80 minus there you substitute. Okay. You will get P1 and P2. Equilibrium price. Next. One more also we have to find out. This is maximum profit. Now equilibrium price. Equilibrium price. P1 is equal to, what is the equation for P1? 80 minus 5x1 we got. So 80 minus 5 into x1 we got 6. So this is 50. This is the price you should charge in market 1. Price 2. 180 minus 20x2. So 180 minus 20 into, what is the x2 we got? 4 we got. So 180 minus 8 is 100. So 100 rupees at market 2. So 50 and 100 is the equilibrium prices. These are the prices you should charge at which profit will be maximum. I hope you understood these steps. So this question is recently asked in exam also. So we have done this scenario also. So both these scenarios we have done. What are those two scenarios? Multi-market scenario with different prices and multi-plant at different costs. So these are the two scenarios we have got. These are very, very important. These are the two questions which you can expect generally. Very important from examination point of view also. Now, I will show you one exam question, recent June 2025. If you see, business application of Maxima and Minima only they have given. See this question, what they have given. Rolex Limited is a monopolist, can effectively segment the market into two sub-markets. So two markets, P1, P2, represents the prices. P1, P2 represents what? Price here. In our previous question, price was not given, no quantities were given. Here, price they are given directly. So P1, market 1, P2 is in another market is the price, where Q is equal to Q1, Q2. Q is equal to Q1. Q1, Q2 represents what? The quantities to be produced in two markets. These two you can add. Total production of two sub-markets. The total cost function of two sub-markets is given. So this is multi-market, no discriminating price we have to find out required. If price discrimination is allowed, assess the maximum possible profit that can be earned by the monopolist from two sub-markets. So this is the case just now we covered. The only thing is equations properly you should select. Now we will have two revenue equations, no? TR1 is equal to P1 into Q1 and yes, this one. How to get this? Now see directly what they have given. Now P1 they have given. P1 is equal to 400 minus 2 Q1. From this we have to get Q1. Q1 minus 2 Q1 is equal to 400 minus P1. Q1 is equal to 400 by, so this is not 2 plus only, 400 by 2 minus P1 by 2. So this is 200 minus P1 by 2. So this is your Q1. So P1 into, now you can substitute. Instead of Q1, what you can substitute? This one you can substitute. Q1 place 200 minus P1 divided by 2. This will be your total revenue. Okay. Or what else you can do? Instead of doing this also, what is the one more thing you can do? Directly P1 is given, no. You need not again do Q1 also. Be smart now. Directly P1 only you take. What they have given? 400 minus 2 Q1, no. Into Q1. Q1 is the quantity. So directly you do this only 400 minus 400 into Q1 minus 2 Q1 square. This is your TR1. Okay. Then TR2. P2 into Q2. Price into quantity in second market. P2 directly given. In this question directly given P2 equation. So 300 minus 2 Q2 into Q2. So 300 Q2 minus 2 Q2 square. Okay, then total cost equation is also given. Total cost is equal to 3000 plus 60Q. So first we should do first order derivative. MR1 we should find out. Nothing but D by dx, dq1 we should call it as now because variable is q1 now inside. D by dq1 of TR1 we should find nothing but we call it as MR1. Next, MR2 also we require. D by dq2 with respect to TR2. Then we should find out MC. D by dq of TC because Q we have no variable. So this is the first order derivative. Then MR1 is equal to MR2 is equal to MC. So equate MR1 is equal to MC and MR2 is equal to MC. Then you can solve for what you will get in this. Q1 and Q2 you will get. What you will get? Q1 and Q2. Then again what? Apply second order derivative. Apply the maximum condition. Same. So this is what recently asked. So this is your multivariable optimization concept, my dear students here. So in this also, first one, what we have done, steps we have seen. What are the steps for multivariable optimization? So how do you know that it is multivariable? In the equation, if you have more than one variable, like x, y, then you realize that there are multiple variables. So what are the steps here? First objective function as it is, then when you are doing partial derivation here, for this partial differentiation is applicable. First time With respect to first variable, you do differentiation, assuming other one as constant. Second time, second variable differentiation, partial differentiation with assuming first one as constant. This is your partial derivatives. See, even though partial derivative is there, if you see our questions, we did not apply partial derivative. With first derivatives only we solve the problem or not, that is the advantage. Okay, we did not apply all these steps. In fact, the two problems we have done, even though multiple variable scenarios only, but we were able to do it with the derivatives only. Even though these are the steps here, but we were able to do with that equation only, that is derivatives only, we could finish off the problem. But anyhow, two variables, if you have first order partial derivative, two times you have to do it with respect to one variable, with respect to other variable. Then solve for x and y. For that, you need to equate with 0. Then again apply second order partial derivatives. For each equation now two times again you will get no. Only thing is last one, second one equation only with respect to y if you do, that is sufficient. Once you get these values, substitute x and y values in that. And here name them as A, B, C and find D value and then interpretation. So for this I have done one question. For partial derivative also I have shown you that illustration. Then in this multivariable monopolistic form, how to get equilibrium, that is profit maximization in two different scenarios. So that is students that is multiple variable optimization. Now these two scenarios, single variable and multiple variable in unconstrained environment we have done, that is assuming that there is no constraint. But in practical world we have even constraint also. So we have in this syllabus even with respect to constraint also, that is single variable with constrained with constraints, that is with restrictions. In our syllabus we have, but I advise you to not to study that for your next coming exam, December exam. Whatever we have covered so far, if you complete up to here, if you complete, that would be more than sufficient. All right. If you practice up to here, that will be more than sufficient for your exam. So thank you guys for holding on to this much time. I took more time, no doubt, but whole concept I covered in this. That is what you should remember. So please follow this notes. All the questions also have included here. The solutions also for multivariable optimization. Practice them. Thank you.